Welcome class to Chapter 15 on correlational tests, the Pearson R, and the simple linear regression. Here we go, correlation and causation. Correlational studies can help us test hypotheses about relationships between two or more measures of behavior to determine whether the measures change together or whether they can predict one another. But we must be cautious about the conclusions we make from the data collected in correlational studies, and that's why we use experiments, right? Experiments are designed to minimize other possible explanations for results of the study besides the causal factors in the study. That's why we use, for example, simple random assignment, and where we keep all groups the same with the exception of changing the independent variable, level of independent variable experience, and such like that, what we're looking for to estimate causation, right? And then we randomly assign people into two groups to minimize the pre-existing factors that might occur if we didn't do random assignment, right? If we just threw all the people in the morning that came in, they might be the smarter people that might influence our study on memory or something like that, right? So if we randomly assign them into two groups, what we're hoping is that the pre-existing differences that might skew the results of what we're looking at, our independent variable, will be really distributed across each group because we're randomly assigning them. So the idea is that we'll have equally smart people in each group, for example, for our memory test, if we felt that smartness was going to help with memory tests. In correlational studies, we cannot control for these other explanations as we can in experiments, right? As well as we can. Thus, we cannot draw causal conclusions in correlational studies as well as we can in experiments. We really can't draw very many causal conclusions at all in correlational studies, but it can give us an idea of things that co-vary, and then we can do experiments on them later. There are really two big problems with correlation as it relates to causation, and they are the directionality problem and the third variable problem. Directionality problem really talks about which causes which, and you're not able to, in a correlational study, you're just seeing which one co-varies with the other. And you're not able to using an experiment to kind of figure out these questions. I use the example of sleep and stress, or lack of sleep and stress. Which causes which? Does a lack of sleep increase stress? Well, yeah, it seems like it would, right? But does heightened stress increase lack of sleep? Yeah, it may also. So which one causes which? In a correlational study, we're not able to figure that out, and that's called the directionality problem. The third variable problem is another problem that they talk about in the book. And while two measures co-vary together, and that could infer some causation, it doesn't necessarily mean that there is causation. And even if they have a one-to-one correlation, I use the silly example of brushing my teeth every morning and the sun rising in the east. Does that mean that brushing my teeth every morning causes the sun to rise in the east? No, of course not. There are other factors. The sun spins on its axis, it goes around, the Earth spins on its axis, goes around the sun, and that's why we see the sun appearing to rise in the east every morning. Has nothing to do with me brushing my teeth, of course, right? But it does prevent bad breath, so that's kind of nice, and cavities. Statistical relationships, so this is the breakdown of the right part of that big flow chart that was overwhelming at first, but now you're really getting it down. You know that whole left part. And remember that a lot of statistics is just realizing what statistical measure to use for what situation. Now we're starting to look at correlational studies right here, taking a look at relationships. And the first thing that you'll take a look at is whether you are using a ratio, interval, or a nominal ordinal scale. In the next chapter, we're going to go over, if you use a nominal ordinal scale, what to use, which is a chi-square test. But this chapter reviewed the descriptive test that you'll use, which is the Pearson R test, and the predictive test, which is the linear regression test. The Pearson R test is a significant test used to determine whether a linear relationship exists between two variables measured on interval or ratio scales. The Pearson R is a value essentially between -1 and a +1. And it indicates both the size and direction of a relationship between two numerical measures. As you can see right here, there's a perfect negative correlation right here of -1.0. And as you can see right here on your x-axis, which is your predictor variable, and your y-axis, as x goes up, what happens to y? It goes down, right? And that's a negative correlation. That's a perfect negative correlation right here. In contradistinction, you have a positive 1.0, which is a perfect positive correlation. That was a tongue twister of sorts. Alliteration, perfect positive correlation. And as you can see right here, as x increases, what happens to y? It also increases. And so you can see that there's the 1.0 correlation here. Data is really tight along this line here. And the positive 1.0 data is really tight right here, whereas you can see there's no relationship here. As the x increases here, well, some of the y's increase, but some of the y's decrease. So that would show you as no relationship. So hopefully that gives you an example of the way that the data is scattered, if you will, on the scatter plot. And that's what you're looking at, as each measure and how it co-varies with the increase in one level, for example, and does it increase or decrease or have no relationship. The larger the numerical value of the Pearson's R, the stronger the relationship, as you can see right here. And then no relationship is 0. Okay. The sign of the Pearson's R value indicates the direction of the relationship, whereas negative 1.0, like I said, as you increase x, y decreases, and the positive correlation, as you increase x, y also increases. So hypothesis testing with Pearson's R, like previous inferential statistics, we can use the Pearson R correlation to test hypotheses about relationships. For correlational studies, we will predict a relationship for our alternative hypothesis, and no relationship for our null hypothesis. And Pearson's R is a relationship of two different variability measures calculated from the two dependent variables in the data. So step 1 is to state your hypothesis, and in the book they talk about hours of study and exam scores, and obviously the hypothesis is if you increase your study time, that your exam scores are going to increase, so there's a positive correlation there. So the alternative hypothesis, in the population of students, there's a positive relationship between the number of hours that students study for an exam and the score on the exam. This P is the Greek letter rho, and so the population of students is greater than 0 in terms of a Pearson R. And in the population of students, there is no relationship or a negative relationship between the number of hours that students study for an exam and the score on the exam, and the population of students is less than or equal to 0. Okay, so you would be predicting for null hypothesis. There's no relationship or a negative relationship, an inverse relationship between studying, hours of study, and exam. As is typical for behavior research, we'll set our alpha level at 0.05. However, the distribution of R values will stop at a value of 1, +1, and -1. And so the shape will be a little bit different, but will still depend on the sample size in the study. And so thus you'll use Appendix E that will give you the table of critical values for your alpha level. And so they give you an example of collecting sample data, and it looks like you just had 5 subjects in your study. And as you can see, number of hours here, and it looks like that if you have higher hours, looks like it's going to give you a higher score just initially looking at the data, right? So next we're going to calculate the statistics, and the statistic for R is the sum of products, SP, and then it's the square root of the sum of squared. Sum of squares for X and sum of squares for Y, where the sum of squares for X is the sum of squared deviations for one of the dependent variables. One appears on the X-axis of the scatter plot, and the sum of squares Y is the sum of squared deviations for the other dependent variable. The one appears on the y-axis of the scatter plot. Reminder, find your values that you need. Remember, mise en place, and so that you can just plug in the values into the equation. Make it simple, right? Take a deep breath, right? There's your equation, and all you have to do is find the sum of products. You have to find the sum of squares for your predictor variable and the sum of squares for your response variable, and then multiply them and take the square root. If we're interested in predicting one variable from the other, for example, ours study predicts final exam scores, then the variable that predicts is our x variable, also called the predictor variable. I know I just reviewed this, but this is just a reiteration of it. And the variable being predicted is our y variable, also called the response variable, and that exists on the y-axis. So number of hours, as number of hours increase, what happens to final exam scores? Ooh, looks like a pretty nice correlation there, huh? It does. Positive correlation. So let's see what exactly it is, right? And so we're going to calculate the statistics. You already know how to calculate the sum of squares in previous chapters, so I'm not going to go over that, but I am going to go over the sum of products. In the book, I noted that it mistakenly said that it was the sum of the products of the square deviations. It is not, and I let you know that in an announcement. But anyway, so the sum of products is the sum of the products of the deviations with x and y from their means. So if you want to take a look at that, the sum of products and how it's calculated here, you have the number of hours studied and final exam scores right here. And so we're going to take 6 minus 3.6. So 3.6 is the mean for the number of hours studied. And then you're going to take 96 and subtract 81.2 from 96 right here. And 81.2 is the mean for the final exam scores. Okay? So we're just going to plug those in, right? And that's the equation right here. X is the scores. M sub x is the mean of the scores. And notice 6 minus 3.6, boom, times what? Y, final exam score, associated final exam score, right? You're going to multiply by, minus 81.2, which is the mean of the final exam scores. So we do that, plug that in for the next one, 1 and 72, right? 5 and 88. And I just keep, and then 3.6, 81.2, notice that they're the same. And I just keep on plugging in that equation, right? Then you have to do the math, and you're going to do your, respect your PEMDAS, right? And you're going to do the math, and you end up getting 76.41 for your sum of products, okay? So doing the math right here, that's 2.4. That's 14.8, right? And you multiply those and you get that, and so on. Okay, makes sense? Step 4, okay, so you're going to calculate your statistics. We had 76.41 for our sum of products, and they gave us these values, so we are just going to just plug those in, and that gets us to 6760.96. Divide those two, and that gets you 0.93, which is your Pearson R value. Note that the numerator, the sum of products, will make the Pearson value either positive or negative. So the Pearson R value, our critical value that we're going to find, is your degrees of freedom for Pearson R is n minus 2. Not n minus 1, but n minus 2. So how many people did we have in our study here? It was 5, right? So 5 minus 2 is 3. So we're going to find degrees of freedom 3 right here. And 0.05 is right there for a one-tailed test, right? And this is a one-tailed test. We're predicting improvement, right? From numbers of hours study. We're predicting improvement, not either way. It can't go either way. That's not our prediction, right? So therefore, the critical value for the degrees of freedom of 3 is 0.805. And remember, our Pearson R value was 0.93. And 0.93, remember we need to get past 0.805, right? Here we go, on our way to 1. And then we passed 0.805, and we got to 0.93, which is almost near 1, right? And so that's definitely in the critical region. It's a very rare score, right? If the null hypothesis were true, it makes our null hypothesis look ridiculous, right? And it shows that if you put in some serious study time, that your exam scores are going to definitely be, or there's a high association between the two, right? Not causation, but there is definitely an increased association. You can see how tricky it is or seductive it is just to say that there was an effect when all you're saying is there's a high correlation between the two. Okay, how to read Spss output on the Pearson test. The Pearson R value is in the first row, and the sign that indicates, of course, the direction of the relationship. So you can see right here that the, let's see, for the number of day, it's negative 0.90. Negative 0.90. This was this study where they had, I think it was how old you were and whether or not you'd return some card that they asked you to do in some experiment. And it seemed like it was the inverse, that the older you were, the more likely you were going to be respectful or follow the rules, right, and return it. And so there was a high negative correlation. The older you were, the increase in age meant the less days that it took you to turn it in. You turned it in on time. And so the p-value in the second row is right here, which is 0.00. And as I said, the negative inverse correlation in the study as age increased, the number of days it took participants to remember to mail the card decreased. Thus, the older a participant was, the closer they remembered to mail the postcard to the date requested. Okay, so now we're going to look at regression analysis. Regression analysis predicts a score on one variable with a score on another variable. Imagine a straight line that passes through the data points that is close as possible to all the data points in the graph. Regression analysis will give us the equation for that line. And the equation of a best fit line is y equals x times the slope plus intercept. Y is a score on the y variable, or on the y-axis, and x is a score on the x variable, on the x-axis. The slope is the amount of slant of the line, and they denote it as b. And the intercept is the value of y where the line crosses the y-axis, and it's denoted as a. Okay? You end up with numeric values for the slope and the intercept. That's what we have to solve for. Okay? With the x and the y remaining as variables, where you can plug in a value for x, that predictor variable, and you can get a predicted outcome for y, the response variable. And they give the example of the exam scores, and this is what they ended up finding for the regression, linear regression, the equation for it. If the sum of products is positive again, then the slope will be positive and vice versa. The formula for the slope right here, b, remember, is the sum of products over the sum of squares for x, and the formula for the intercept right here that you'll plug in so that we'll solve for, and they call it a, is the mean of y minus the slope, so we solve the slope and then plug it in here, times the mean of x. Okay? So let's go into it. Okay, so remember the equation for linear regression is y equals x times the slope and the intercept. We need to solve for slope first and solve for intercept, and then it's just a matter of we have our equation, and we just plug that into the final equation right here. That's what we're going to get. So how did we get 5.03 for the slope and 63.09 for the intercept? Well, we were given these values right here of the sum of products and the sum of squares for x, and we just plug those in and we get 5.03. Woo-hoo, right? And then the intercept, we were given those values too. Remember, that's A. And that's going to be, remember, the mean was 81.2 for y, 5.03 for the slope that we already solved for, and 3.6 for the mean for x. And we get 63.09. And then it's just a matter of plugging in the value for slope right here. Remember, y equals x times the value that we just solved for slope, plus the intercept, which is the value that we just solved for the intercept. These are the final exam scores, and this is the regression line example and the equation right here. Regression line is very useful if you want to use this equation to predict your outcome, the y response variable, based on a certain value of an independent variable, the x, the predictor variable. Suppose you plan to study for 6 hours for the exam. What score do you expect to receive with this amount of studying? You can just plug in 6 right here for your x value, right? Because remember, this is the equation that we found. And that's the score that you expect to receive, a little better than 93%. But how accurate will your prediction be? Data points that are close to the line, if you have that, the prediction will be good. Data points that are spread out across the graph and the line does not get very close to them, prediction is not so accurate. I think in the next slide I have that right here, yeah. So as you can see here, for the fit statistic, right? So if your data points are all over the place, not going to be that accurate. Data points close to the line, accurate. Your predictions are going to be accurate, okay? The R2 is the symbol for the fit statistic, indicating how well an equation fits the data, like I said. And so to find that, you simply square R. And if you'll remember, we found the Pearson R for that data, for that study, was 0.93. So we square that and we get 0.86. Fit statistic is a measure of how much variability in the one measure is explained by the value of the other measure. So what we can say right here, using this fit statistic of 0.86, is the above equation means that 86% of the variability in the final exam scores is explained by the number of hours that students studied for the exam. This represents a good fit to the data and tells us that our predictions, looks like I have predications there, our predictions will be fairly accurate. The book recommends 90% or higher for the gold standard. And different charts like I talked about with the high fit statistic and lower fit statistic. And then reading the SPSS output for linear regression, right here you can see that the fit statistic is 0.811, this output here. And then in terms of figuring out the values for your linear regression, you have y equals x times the slope plus the intercept. What we have to do is find the slope in this output right here and find the intercept. And as you can see, the slope right here is in this B column, and it's the line with the predictor variable, which is the age in years, and you just plug that in right here. And your intercept is the line with the response variable, which is labeled as the constant in the column B, and that's 9.209, and you just plug that in there. So that's kind of hard to remember, so you'd probably have to have some notes and then kind of plug it in that way. Nonlinear relationships between variables can exist that are not functionally linear. So you'd be like, okay, I got this linear regression, right? And that means my stock that I'm following is just going to keep on going up, right? All I have to do is plug in that value and it's going to keep on going up. Well, the reality is things don't always just go like this, right? They may be inverse, so they may go up and then they may go down. Hopefully, if it's your stock or something like that you hope to go up, it just keeps on going up. But there are, in reality, things that have an inverted curve, like a parabola, for example. And these are nonlinear relationships where the linear regression model would not be helpful for you. And that's what the book just talks about at the end right here. Suppose in our study we had measured the student's anxiety level with a 1 to 10 rating just before they took the final exam. You get those scores right there. They give the example. And as you can see, the data points look more like an inverted U shape or an upside down parabola than a single line. If this is the case, then the quadratic equation is a likely better fit to these data than a linear equation, which is in college algebra that you'd be studying there. You're taking this class, so probably not going to encounter that, so you have to refer to the formula for that. Looking at a scatter plot of your data points is a good idea before deciding what kind of equation you want to fit your data if you do not have a theoretical prediction about the form of the relationship before you start your study. And I hope that was helpful, and I will see you next week for the next chapter.